Allan Fordy from the University of Leeds. Now here we will be talking about integrable maps which preserve functions with symmetries.
Whether I'm setting this up correctly. Okay, thank you. So Andy, of course, was under the impression that I was going to give the second half of his talk. So unfortunately, there was no coordination made there. We did do this in Japan once, but we didn't coordinate this time. Okay, so this time, where's it gone? Actually, I'm going to talk about something completely different. Some work I did with Pavlos Kostakis, who was my student at one time, but is now working in Sydney. And, well, it's based on this paper here. We got does that work? I don't see a red light. Does anyone see a red light? Is it easy?
Beside, there is a switch.
Oh, is there a switch? Oh, right. Ah, yes, okay. Maybe it was off. Yes, now it's on. Good. Yes, that works. Good. Okay, this paper. Okay, so I'm going to explain how certain types of mappings on, well, mainly on four-dimensional space, but there's an example into 6 dimensions, can be reduced down to lower dimensions. Well, that's okay, reduced to 2 dimensions, but we give a way of reducing 2 different maps to the same space, and then they commute. So it's a way of producing commuting maps, in fact, on the plane. So let me explain this. Okay, so let's just consider this particular example, which came from one of our earlier papers, or from our earlier paper. So you just take these two Hamiltonians, and you notice that this Hamiltonian is invariant under this simple involution, and you can create another involution that is sort of the first half of the QRT type construction of row x, which is just by keeping y fixed and switching x around. And if you do that, then you create a map, right? Well, you create a map which is a composition of these 2 involutions. They don't commute, these involutions, and therefore you have a map which generates and has an infinite orbit. This particular map has this well, it's anti-invariant. This volume form is anti-invariant, so it combines itself. So I'm going to show that this, in a moment, see these Hamiltonians, they have a certain symmetry property. So let's look at this simple vector field, just for x1 minus x2 minus y1, y2. It has these invariants. Well, it has 3 invariants, independent ones, but if I write down these 4 polynomial invariants and then just note that it has this relationship between them. And under these invariants, I, 3 and 4 interchange. Under this simple involution, I and 3 and 4 interchange, and 1 and 2 remain invariant. And these 2 Hamiltonians that I wrote down can be written in terms of these invariants, because these are this. If you take x dot grad hi, you get 0. So these can be written in terms of these invariants. And under this map that I wrote on the other page, this vector x goes to minus itself in the new variables. And if you choose these coordinates, so this is just a standard reduction. If you just choose nice coordinates, so nice coordinates are going to be these invariants, because h1 and h2 are written in terms of these invariants. So we choose a couple of these. h2 is built out of the invariants, so we choose u2 as being h2. And one of them has to be non-invariant, right? So we choose y2. And in those coordinates, well, you can just calculate. You get omega 4 comes down to that. X now becomes v2 dv2, and h1 looks like this. And then on under this map, the details of which don't matter, but that map that I wrote down, the subspace of invariance is left invariant, of course, because it was designed like that. And in fact, I chose U2 to be an actual constant, an invariant function of the map, not just invariant of the symmetry. So you can reduce omega 4 down to a three volume where the V2 disappears completely, because we've now dropped down onto the space of invariance. In fact, space of invariance of X, capital X. So in this space, you just get a two-dimensional map, which well, you get a four-dimensional map. But the first of all, this three-dimensional space is invariant, and since U2 is itself a constant of the motion, then actually it drops down to being a two-dimensional map, together with U2 being constant, and together with V2 transforming in this very simple way. So although we don't have a four-dimensional, I can't say that the original four-dimensional system was completely integrable in the Liouville sense. I mean, the map sort of completely integrable in the Liouville sense, but at least it goes into this sort of triangular structure. So you've got a two-dimensional map together with just a constant, together with a very simple evolution here. This particular map is just the QRT map you would get from this H if you just calculate it straight from the H. Okay, so that far, that much is just straightforward reduction. There's nothing particularly interesting on its own. However, if we now just make what looks like a very trivial change of so this minus has gone to plus, this plus went to minus. That's the only difference. But now we have another set of invariants which is slightly different. All right? So the two of them stay the same, and these ones got a slightly different form. They still satisfy this property, and they still still switch like this under this simple involution. So now, if you and in terms of these invariants, so now we write down the same h's, but in terms of the invariants, and then rewrite this in terms of x's and y's. You get different. Well, there's only two changes here and here. But now, if you go through the same procedure of building this map, which I call row x before, but just switching x1, x2, x1, x2 tilde, and y1, y2 getting fixed, then you get a different, and compose it with this involution, wherever it's gone, this involution, then you get a different map altogether here. But the same procedure for reduction works, so you can go down through the same. You can still this volume form is still anti-invariant. This vector field still goes to minus itself under the map. The H, because of the way it was built out of the invariance plus the invariance satisfied the same condition, this constraint here, because you have to eliminate gamma 4 from this, comes down to the same function here. So we drop down to the same, we get the same reduction, and we get the same three form here, right? So this two form is what's going to be important. So in fact, so that map also has the same structure of being two-dimensional plus one-dimensional plus this simple evolution of V2. But on this level surface, U2 equals K, then you have another map. U1 hat is this, V1 hat is this, different from the tilde map, the U1 and the V1 tilde. They still preserve this function, they still preserve this symplectic form, and on this two-dimensional space, these two things commute. So for some reason, which we don't really understand, I mean, when you drop down to this 2 dimensions, you can you create two maps which actually commute, which is a rather curious structure. So whilst writing this talk, I was just trying to look at what four-dimensional Poisson brackets might exist. Oh, I don't know that an invariant one exists, but here I just noticed. I happened to notice that that H1 and H2 as given. Well, this is the first case. It works for both. H1 and H2 as given, they happen to commute with respect to the canonical bracket. And then you can write down the Poisson tensor with this, which is just, zero identity minus identity 0, P naught. And with respect to this Poisson bracket, the vector x, our symmetry vector, is just Hamiltonian with respect to this Poisson bracket. So the invariance of x, which x dot grad invariant is 0 by definition. So that means that's equivalent to saying that the invariants just commute with respect to this Poisson bracket with H2. So any function built out of these invariants will automatically commute, of course, which is why this commutes. And P naught has particularly simple, so here it has a very simple structure, just constants, of course, but here it has a non-constant but another structure if you choose these coordinates, which are the ones that I chose before. Right? Furthermore, this birational map, so phi is birational. I mean, you could calculate both its inverse is rational. So you take any Poisson tensor and any map, you can create it just goes to some other Poisson tensor. It doesn't have to go to itself. So this time it's not invariant, so it doesn't go to itself. It goes to some other ones, which I'll just call P plus minus 1. Then if you map again, it'll go to plus minus 2, and so on. So you get an infinite number of Poisson brackets, basically. I don't know how many of them could be considered as independent, but anyway, you get I'm not quite sure what that means. But you get an infinite number of Poisson brackets, and with respect to each of these Poisson brackets, these two functions commute. So it's just a little, that was, and if you write in these coordinates which we chose before, then you get an invariant 2x2 block, which is the equivalent Poisson bracket to that symplectic form. So you can see that if you start, when you transform the canonical one to these coordinates, you get this. If you go backwards, you get this. If you go forwards, you get this. But you see that this block remains fixed. But these things change. So I don't know how many of these could be independent, but anyway, it produces all these maps. So it's not so as a Hamiltonian system, this is completely integrable. But as a map, of course, this doesn't tell you that the full four-dimensional map is integrable. It just tells you that in a Liouville sense. But because this 2x2 structure is kept fixed, then the two-dimensional system is. And that same thing happens with the second map. So it's a sort of probably going to be a type of explanation of what's happening. In fact, anyway, let me continue with the main topic, which is okay. So what have we got? We start with some vector fields. I'll just write down the one I've already used, but we have several different vector fields which can be used. A simple vector field like this, so you can build a simple set of invariants, and in this simple set of invariants have some simple transformation properties under a given involution, which isn't always going to be x, y. It could be 1 switches with 2. But, so there will be these various things given, like an x and an iota x, y, or iota 1, 2, or whatever, and then you'll have some properties like this, and you'll also have a constraint, because of course there are only 3 of these are independent. And then you build some sort of Hamiltonian, which I gave you an example of, out of these invariants. And going through the procedure I spoke about, you can reduce to two-dimensional space. Well, reduction to the two-dimensional space depends upon this constraint here. So you have to choose specifically. So you get a different. when you go down to 2 dimensions, you get a different form of the H depending upon this structure. So if you, in the case, 2 cases that I gave, I chose, well, if you choose something where these invariants have the same constraint, then you reduce to the same Hamiltonian, and then you'll get this phenomenon of reduce into 2 maps which preserve a Poisson bracket, well, preserve a symplectic form, preserve Hamiltonian, and commute. So let's see. However, if I want to write down the invariance of this map, of this vector field, then of course I can choose the ones I chose before, which were sort of just things like x1, x2. Well, they're all polynomial ones. Yes, I could choose. Choose the previous gamma 1, gamma 2, gamma 3, gamma 4 that I previously had, and now I can because gamma 1 and gamma 2 remain fixed, gamma 3, 4 interchange. If I just divide by gamma 1 here, say, I don't change this condition, this property here at all. But I do change this property. So it will reduce to a different Hamiltonian on 2-dimensional space. So for instance, if you do what I just said, then we'll be choosing as gamma 1, 2, 3, 4. Well, the first 2 are the same, and then gamma 3 is this, gamma 4 is this. And then they satisfy this property, which is different from before. But they still have this property with respect to iota xy. And if you choose these functions in terms of gammas, then of course you get different functions here. Well, this stays the same. Here you get different functions. But still you get the same procedure works, but now you reduce to this Hamiltonian, say. And if you do that, and then you do that with these 2 different vector fields, for instance, we choose 2 different vector fields, then you can produce 2 commuting maps. But as it happens, this time, so you produce 2 commuting maps this way, but neither of them is the QRT map which you would obtain if you just started with this. So you get a 3rd one. Of course, I'm not saying that these 3 maps should be independent. It's very difficult to determine when 2 maps, even, let alone 3 maps, have any function are related by some. Obviously, if you take phi and phi squared or something like that, then it's easy to see. But if it's some complicated relation between them, it's almost impossible to see. It's not unlike with vector fields. Vector fields are just linear things. This basically the linear operators. You just just have to look at a linear space basically. But with these functions, with maps, it's very difficult to determine when 2 maps are independent. You can look at the orbit that you plot, and if the plot go in different sort of orbit, then you might convince yourself that they're independent. So I guess the 3 of them are not independent, but I don't know of any relation between these. Okay. So there are a lot of choices actually. You choose the vector field x, and there's several of those you can choose. You have to choose from the invariance of this. You construct some functions hi. Initially, we're only any old functions of gammas will do, but actually, when you're looking at these involutions that you're constructing from taking the one I call rho x, then you find that quite often you get non-rational maps. You get square roots, cube roots, or whatever coming into there. So there are some constraints on how you. So it's not entirely known in advance if you start with some particular functions, h's, whether you're going to be able to construct a nice rational map. And also, okay, if I, like before, I started with some functions and I just said, well, let's see what we get. You can do that. But if, for instance, you pluck you see some map, like the Adler Yamilov map, which was spoken about earlier today. If you see some such map and you want to fit it into the scheme, then you have to be a little bit more clever about choosing your involutions. Right? So So you may have to use something other than row X, a more complicated involution. But if you can find such, if you find you choose an H which is invariant under simple involution plus something row X or something else, then you can decompose. Then if you can find such pair of involutions, such as some map that you see in the literature is can be decomposed like that, then you can try and perform this construction. Yeah. So in particular, if you look at this, well, today Satiris spoke about this. Yeah. So you can just start with these two functions. These two functions actually do have this property with the involution iota 1, 2, 1 and 2 switched. They're invariant with respect to this vector field. And if you compose this involution with this strange looking, so it's different, not row X, but this thing, this involution, then you construct this this map, which is called the Adler-Yamalov map. But it's Yang-Baxter, but it's not involutive. Most Yang-Baxter maps seem to be involutive, but this one is not. Well, most ones that people have spoken about, anyway. So in this case, you see we've got these two functions. So we can just go through this procedure. I'm not going to do that because I don't have time, but you go through this procedure, then you can produce, you find that there's this common so you get two commuting maps with a common invariant function. The common invariant function is given by this H. This is the Poisson, the symplectic form. Actually, this Adler-Yamalov map is already has a symplectic form in 4 dimensions. And actually, if you write this symplectic form in the UV coordinates in 4 dimensions, then it becomes the sum of this minus maybe du2 d wedge dv2 over v2. So this is actually just a reduction of the Hamiltonian of the symplectic form that's already known, in fact. And then using these two different vector fields, so this is the one that we started with, and then another one, then you construct two different maps, both of which preserve this Hamiltonian, both of which preserve this symplectic form, and they commute. So, so that's basically the idea is that you can reduce down from, well, in 4 dimensions it's pretty clear that if you've got a pair of functions which have this symmetry type property, because basically you need a symmetry, either you need a symmetry plus use one of the Hamiltonians to reduce down to 2 dimensions. Yes, so it's a simple process. So you can see that if you've got this structure in 4 dimensions, then you're almost certainly going to be able to reduce down to two dimensions. And if you do this with 2 different x's, you'll get commuting maps in 2 dimensions. In 6 dimensions and higher, there are some complications, but it is possible, and we gave an example of this. So you're going to start with 3 invariant functions, and you need to construct 2 symmetry vectors, one of which will be this very simple one, and one of which will be more complicated. And you use 2 invariant functions plus 2 symmetry vectors. That will reduce you down by 4 dimensions, so it will get you down to 2 dimensions. Yeah. So in 2 dimensions, you then obtain some invariant symplectic form and invariant one remaining function. It's fairly easy to write down symmetry vectors because you just have to solve some equations, some simple linear equations actually. But finding ones which satisfy this property, which you need for guaranteeing invariance of the final symplectic form, then it's more tricky. And you also need so these vector fields, these 2 vector fields. Well, the first one is easy to check any of these properties, but the second, to find a second one, it has to satisfy certain properties. So, for instance, if you're going to drop down from 4 in... I've done this for 4 dimensions, but anyway. If you're going to drop down from 4 dimensions to 3 or from 6 to 5, then to guarantee that this is satisfied, then which you will eventually need for a symplectic form, then then you require this Lie derivative to be 0, because this Lie derivative, if you calculate, it's just because this term is automatically 0, this becomes this. Yeah. So in terms of some volume form in n dimensions, that's just some divergence condition. So these vector fields have to have a certain divergence condition. And so as I just said, in 4 dimensions, it's fairly straightforward. You just drop down to, you get x hook omega 4 will give you a 2-dimensional omega wedge dh2, where dh2 is the Hamiltonian you use to reduce down to 2 dimensions. Different x's, well, lead to different reductions, but with the same invariant function, same symplectic form, so you get, and you get commuting maps for some reason. In 6 dimensions, the general structure is you've got 3 invariant functions, 2 symmetry vectors, you reduce down from 6 to 4 and by doing this, and the 4 has a special structure. It's omega, which is going to be the symplectic form on 2 dimensions, wedge dh2, wedge dh3, or dh1, d3, whatever. This symplectic form will be of some structure like this, and the map will, well, so we give an example of this in the paper, but I didn't write it here. The map, this is invariant under the map, and so is the function that you drop down, that you reduce. And again, you can use different vector fields and get more. So you can do this reduction again and get commuting maps within 2-dimensional space. In general, of course, you can't expect a 6-dimensional system to drop down to 2 dimensions. Certainly, if you've got this first vector field, it'll drop down to 4, and then finding a second so-called good symmetry, whether it exists or not is another matter, and map will only reduce beyond 4 dimensions down to 2 if you can find this particular symmetry. Otherwise, you only go down to 4 dimensions. Okay, so I'll stop there anyway. Thank you.
In one of your examples, you mentioned the Yang-Baxter property. What about the other examples? Can they have the Yang-Baxter property, consistency property?
Well, we give a couple of examples of Yang-Baxter. Actually, we extracted a couple of examples out of this paper of Sotiris and Sasha Mikhailov, both of which were Yang-Baxter maps, which can succumb to this procedure. But actually, the Yang-Baxter property has, as far as I can see, nothing to do with whatever I'm doing here. So it just happens to be a fact that these 2 maps have the Yang-Baxter property. To start off with, in the 4 dimensions, they have the Yang-Baxter property. When you drop down to 2 dimensions, they lose this property anyway.
These Poisson tensors are compatible in the sense of bihamiltonian theory.
Sorry?
Poisson tensors, P0, P1, and
those that sort of set. Well, yes, they seem to be. If you take a pair of these and take the sum, it still satisfies the Jacobi identities. So I don't understand why. I mean, I don't understand how many of these Poisson brackets could possibly be in any sense independent. I don't know whether you. I was asking both Andy and Yuri whether they know about this, but.
I mean, just a quick comment that generally this situation is rather common. So in fact, in the stuff that I talked about, when the matrix B is degenerate, then you have something rather similar going on. That you have a torus action, and then you actually get a symplectic map by taking the quotient by this symmetry and by the symmetry group, and also some examples of Quispel and Van de Kamp and some of their co-workers with reductions of, I think, discrete ADV or Frank Gordon, they have a similar
No,
story.
no, the reduction is nothing special. Yes, I mean obviously if you've got you can reduce quite. For me anyway, the interesting thing was that actually you just by making some apparently trivial change of this initial vector field, you obtain two maps which actually commute on the, when you drop down to 2 dimensions. That was a rather strange, for me, a rather strange property. I mean, I don't understand why that property holds, but it just does.
If there are no more questions, then let's thank the speaker and we'll reconvene.